Hi guys, you are welcome to today's video. We'll be looking at dimensional quantities. But before we go to the applications or use of dimension, let's quickly derive more of dimensional quantities. They are the dimension of sub-quantities. In our last video, we were able to do just 10. Let's see if we can quickly do another 10 before we go to the applications. So we are still on dimensional analysis. Dimensional analysis. Remember, in the last class, I said the process of obtaining dimension of some quantities is what we call dimensional analysis. And we've obtained the dimension of 10 quantities. Let's look at 10 more. Let me call it 11. Let's look at specific heat capacity. Specific heat capacity. We use small letter C to represent that. And don't forget what I said, that once you know the formula where that quantity is present, then you can obtain the dimension from that formula. You can get this from using quantity of heat gained or supplied by a body, and that is given by Q is equals to MC change in theta, mass of the body, specific capacity, temperature difference. Okay, so from there, C will give us Q over M change in theta. So that's the formula I'm using. That is quantity of heat over mass times change in temperature. Okay? So let's obtain the unit of that. Unit now. Unit of quantity of heat. Heat is a form of energy, and all energy are measured in joules. So quantity of heat is measured in joule, mass in kilogram, temperature difference in Kelvin. So the unit becomes joule. If kilogram goes up, it becomes per kilogram, then per Kelvin. Joules per kilogram per Kelvin becomes the unit of specific heat capacity. Then to get the dimension, we need to get the base unit first, right? And I said base unit simply means expressing this unit in terms of the fundamental units. So let's look at base units. Base unit of joule. Joule is unit of work done. Work is force times distance, right? Base unit of force is kilogram meter per second square. In the last class we did that. Then distance is meter. We have kilogram meter square per second square. This becomes the work unit, the base unit of work or energy. Okay? So that is what we call joule. So we have kilogram meter square per second square. That is for J. Then we have per kilogram per Kelvin. Kilogram and per kilogram we cancel out. So we are left with meter square per second square per Kelvin. Right? So this is the base unit of specific capacity. Then for the dimension now, we turn the base unit to dimension. Dimension of meter, capital letter L, then you square it. Dimension of seconds, capital letter T, this by minus 2. Temperature is theta. So that becomes the dimension of specific heat capacity. Let's quickly look at another one. Let's look at angular momentum. Angular momentum. We use L for it at times. Angular momentum. And what's it all about? Angular momentum is also called moment of a momentum. That is the product of linear momentum and perpendicular distance. And perpendicular distance is the formula. Linear momentum by perpendicular distance. And don't forget that linear momentum is mass times velocity. Okay? Then time perpendicular distance. So the formula becomes m VR. Mass times velocity times perpendicular distance. M times V is called momentum. Okay? So mvr is the formula we are using to get angular momentum. Units now. Unit of mass is kilogram. Velocity is meter per second. Distance is meter. So we have kilogram, meter times meter will give us meter square per second. Alright? The base units remain the same. That's also kilogram, meter square per second. Then the dimension now. The dimension becomes capital letter M, L square, 3 to the power minus 1. Okay? Let's look at another one. Let's look at electric charge. Electric charge. We use Q for that. Remember, Q is what? Current times time, IT. Do you remember that? Q equals IT. Probably in electrolysis or in electricity. Q equals IT, that is current times time, is the formula for charge. Okay? Units now. Unit of current is ampere, time is seconds. Okay? So unit of electric charge is AS, or what we call what? Coulomb. Coulomb is the unit of charge. So this becomes the base unit. The base unit of charge is AS. Unit of charge is coulomb. So 1 coulomb is the same thing as 1 ampere second. Alright, dimension now. Dimension of ampere is capital letter I, time capital letter T. Okay? Let's look at another one. Let's look at potential difference. Electric potential difference. Electric potential difference. And potential difference formula is work done over charge. Work done over charge is a formula for potential difference. You can use any formula for potential difference, be it in gravitational field or in electric field. Okay? So let's look at that. V equals W over Q. You can also use capital letter Q for charge. No problem about that. So units now. Unit of potential difference is volt. Volt. Or we can go from the formula. Unit of work done is joule. Charge is what? Coulomb. Coulomb. So joule per coulomb. So the unit becomes joule per coulomb or volt. 1 joule per coulomb is the same thing as 1 volt. Okay? Therefore, the base unit. Let's break this one down. Joule. We've used that before in our specific capacity. So joule is kilogram meter square per second square. You know, joule is force time distance. That's unit of work done. Force time distance. And the base unit of force is kilogram meter per second square. The time distance, we give you meter square. We use it in that place in specific capacity. Okay? Coulomb is AS. This is base unit of coulomb, AS. Since time power of minus 1, so all this one we have power of minus 1. Okay? So we have kilogram meter square per second square. The power will affect the content of the bracket one by one. So we have A raised to power minus 1, S raised to power minus 1. So we have kilogram meter square. Seconds, there are 2. Per second square times per seconds will give us S raised to power minus 3 from law of indices. You add the power. You take the base, add the power. Minus 2 plus minus 1. That will give us minus plus times minus is minus. So minus 2 minus 1 will give us minus 3. Okay? So we have kilogram meter square S raised to the power minus 3, A raised to the power minus 1. That becomes the base unit of potential difference. The dimension now, dimension, kilogram is capital letter M, A raised to the power 2, T raised to the power minus 3, I raised to the power minus 1. Then the next one, let's look at resistance. It's another common one they ask. Resistance. From Ohm's law you can get that. Remember Ohm's law is V equals IR. So R will be what? V over I. So that is potential difference over current. And then God will just do the potential difference, right? So units now. Unit of potential difference is joule per coulomb or volts. Volts. Unit of current is ampere. So resistance is volts per ampere, or what we call resistance is a specific unit called ohms. Ohms. This is how we represent ohms. Ohms is the unit of resistance, or volt per ampere. 1 ohm is same thing as 1 volt per ampere. All right. Then for the base unit, what is the base unit of volts? This is it here. This is it here. Volts. So let's just lift it. Kilogram meter square. S raised to the power minus 3. A raised to the power minus 1. Okay. That is for V alone. Then times per ampere. So that gives us kilogram meter square. S raised to the power minus 3. A raised to the power of minus 2. Minus 1 minus 1 gives us minus 2. The dimension now. Let's put up the dimension. Kilogram is capital letter M. A raised to the power 2. T raised to the power minus 3. I raised to the power of minus 2. Okay. Another important quantity is capacitance. Capacitance of the capacitor. Capacitance. You know the formula is C equals Q over V. All these quantities, we are still going to do some of them as topic. We still treat them as topics. Okay? So capacitance is quantity charge over potential difference. The charge stored between in each plate of a capacitor divided by the PD between the plates. Okay? So units now. Charge is measured in coulomb. Potential difference is in volts. You see this V for that. So that's coulomb per volt, or what we call farad. Unit of capacitance is farad. Please permit me to rewrite that. Unit. Charge is coulomb. Potential difference is volt. So that's coulomb per volt, or what we call farad. Capital letter F, farad. 1 farad is something as 1 coulomb per volt. Is there from the Faraday, you know, in the electrolysis? So, you know, 1 Faraday is what? 96,500 coulomb. Okay? So the unit of capacitance is farad. Base unit now. Coulomb is for charge, and base unit of coulomb is AS. The potential difference. Base unit of potential difference is, we've done it in that place. Let's just lift it. That's kilogram meter square. S raised to the power minus 3. A raised to the power of minus 1. Now this is our V. But our V is the power of minus 1. So all these ones we have minus 1. Okay? And as usual, the power will affect the content of the bracket one by one. So let's open the bracket now. We have AS, kilogram. If you have it, that's per kilogram, then per meter square, minus 3 times minus 1. That will give us plus 3. So S raised to the power 3, A raised to the power 1. You know, when you're having two powers, you multiply the two powers. Minus 1 times minus 1 gives us plus 1. Minus 3 times minus 1 give us plus 3. 2 times minus 1 give us minus 2. Okay? So we have, let's rearrange this, per kilogram per meter square. S times S raised to power 3 will give us S raised to power 4. Remember law of indices. S raised to power 3 times S. This S is the power of 1. So take the base, add the power. Law of indices. That's S raised to power 4. Okay? Then, what is left? A. A times A will give us A square. Per kilogram, meter square, S raised to power 4, A square. That becomes the base unit of capacitance. So, dimension now. Once your base unit is correct, then the problem is solved. Because if it does the base unit, it turns to dimension. Dimension of kilogram. Then L raised to power minus 2, C raised to power 4, I raised to power of 2. Let's look at another one. Another quantity. Let's look at dipole moment. Dipole moment. I think we might have heard of this in chemistry. It is just charge times separation. Charge times separation. The separation, that's the distance. You can use D for that. You can also use R or use S for that. Charge times distance. So units now. Unit of charge is coulomb. Distance is meter. So that becomes the unit. Then for the base unit, coulomb. Base unit of coulomb is AS, ampere second. Then M. Let's turn that to dimension. So we have dimension of ampere, capital letter I, second, capital letter T, meter, capital letter N, becomes dipole moment. Okay? Let's look at another one, another quantity. Let's look at Planck's constant. Planck's constant. We use K for that. H for that. You know, from Planck's theory, it says the energy is proportional to the frequency, and that will give us HF. Okay, so from there, H will give us energy over frequency. So that's the formula. Energy over frequency. So unit of energy is joule. Unit of frequency, it's hertz or per second. Hertz or per second. Let's use per second. If per second goes up, it becomes second. So we have joule second as unit of Planck's constant. Joule second. So base units now. Base unit of joule, we've done that before, that's kilogram meter square per second square, then times seconds. This is for joules, kilogram meter square per second square. Okay, that will give us kilogram meter square per second times seconds will give us S raised to power minus 1, minus 2 plus 1. Dimension now. Now we capital letter M, L square, then 3 raised to power minus 1. Let's look at another one. Let's look at thermal conductivity. Thermal conductivity. Thermal conductivity. Okay? We use K to represent it. Thermal conductivity. And we can get that from Fourier's law. Now, what does it say? Fourier's law is saying that the rate of heat transfer is proportional to the surface area temperature difference per unit length, the one we call temperature gradient. So if you remember proportionality sign, your constant is the K. So you can get it from this formula. From here now, K will be what? We're going to treat this when we get to heat as a topic. So K will give us QL over CA change in theta. So we can use that formula for it. QL over CA change in theta becomes the formula for thermal conductivity. Quantity of heat, distance between 2 points, time taken, surface area, and temperature difference between the 2 points. Okay? So units now. Quantity of heat is measured in joules. Distance is in meter. Time is in seconds. Area, meter square. Temperature in Kelvin. After you bring that together, we have joule. 1 meter, you cancel 1 meter here. We have just 1 M here. If that M goes up, it becomes per meter, right? So we have, if second also goes up, it becomes per seconds. We have per seconds, per meter, per Kelvin. Another, the normal unit we use is watt per meter per Kelvin. Where is the watt coming from? Joule per second is the unit of power. You know power is what? Energy over time, or work done over time. And unit of work done is joule. Time is seconds. That's joule per second. Power has its own specific unit called watt. Joule per second is called watt. So you can say watts per meter per Kelvin is the unit of thermal conductivity. Okay? Or you leave it like this: joule per second per meter per Kelvin. And let's look at the base unit. Let's look at the base unit. Base unit now. Joule is base unit is kilogram meter square per second square. Then that's for J. We have per second again. We have per meter, and we have per Kelvin. So we have kilogram meter squared times per meter will give us m raised to power minus 1. Remember, m squared times m raised to power minus 1. That's 2 minus 1. That will give us, sorry, m squared. So that gives us ordinary m. Ordinary m. 2 minus 1. That's ordinary m. 2 minus 1 will give us 1. Okay? Per second squared times per second will give us s raised to power minus 3. Okay? Then we have per Kelvin. Kilogram meter per second cube per Kelvin. Dimension now. K is equals to calculator m, L, 3 raised to power minus 3, theta raised to power minus 1. That's become the base unit. I mean the dimension. That becomes the dimension. Okay, number 20. Now, let's look at electric field intensity or magnetic flux density. So that's better. Magnetic flux density. Magnetic flux density. We use B for that. And of course, from the quantity of heat, from the magnitude of the force a charge we experience, if it enters a magnetic field, you can get it out from F equals QVB sine theta. If the charge enters perpendicularly to the field, theta becomes 90. and alternative will give us 1. Or better still, sine, cosine, tan of any angle does not have unit. Okay, so we don't need this one. Let's just go by F equals QVB. So from there, B will be what? F over QV. F over QV. Okay? F over QV. So let's use that. F over QV. So units now. Unit of force is Newton. Charge is coulomb. Velocity is meter per second. So we have, that will give us Newton per coulomb per meter, then seconds. Newton seconds per coulomb per meter, or what we call magnetic flux density has its own specific unit called Tesla. Tesla, that's its own unit. Capital letter T. Tesla. And Tesla is 1 Newton seconds per coulomb per meter. Okay? Base unit now. Newton is kilogram meter per second square. Coulomb is AS. Power of -1. Then we have per meter, we have seconds. Kilogram. Let's open the bracket first. Kilogram meter per second square. A raised to power -1. S raised to power -1. M raised to power -1. Then S. We have kilogram. Meter times per meter we cancel out. Okay? Meter times per meter, this and this we cancel out. Per seconds and seconds we cancel out. We are left with what? S raised to power -2. Okay? A raised to power -1. So that becomes the base unit. Meter per meter we cancel out. This one we cancel out. Good. So dimension now. We look at, that's capital letter M. T raised to power -2. I raised to power -1 becomes the dimension of magnetic flux density. Alright. At this junction, I think we stop here. We'll continue in our next video where we will be looking at application or use of dimension. Please, if you have not watched the previous video, go and watch that, please, so that you can know where we are coming from. And if you have not subscribed, please subscribe, so that when next we upload any video, you'll be directly notified. Thanks.